Hello everyone. The project that I worked on is heart disease prediction using machine learning models. So, heart disease is a major cause of death in United States. There are a lot of risk factors that are contributing to development of heart disease in people. They are high blood pressure, high, high blood cholesterol, and smoking habits. So, predicting them on an early stage is a very difficult task. Uh, since fortunately, there are a lot of clinical data that is available to us, the machine learning community, for building a model and making a prediction system so that it would supplement the expert analysis and allow us to avoid the fatalities before it occurs. Um, my aim of this project is to improve the accuracy of these predictive systems so that there is no fault in the predictions, and that's that's the reason that I took up this project. Uh, the data set that I used was borrowed from UCI machine learning repository. It is called the heart disease dataset. There are actually four datasets available under this main dataset. They are from different locations, like two of them are from Switzerland, and one is from Cleveland, and the other one is from Budapest. The one that I've used is from Cleveland, and in that dataset there are 303 records, and there are 14 attributes. Um, in that also there are six null value records, and initially the data set is in the original form of five labels, 0 through 4, where 0 means that the person does not have any heart disease, and 1 2 3 4 stands for different types of heart diseases. But since the problem that I'm going to solve is entirely based on binary classification, we will not be requiring the labels 1 to 4. So the first step in pre-processing would be converting the labels uh, which are other than 0 and 1 to 0 and 1 to 1 scale. So after doing pre-processing, all the labels are converted to 0 and 1. And also, since there are six null value records, it has to be taken care. And there are two methods by which we can do it. Either we can remove those records from the dataset, or we can replace it by mean values of those attributes. Since this is a clinical dataset, replacing it by mean value would not be a good approach, since it would affect uh, it would affect the prediction accuracy later. So I just removed all those six records, since the number of records is also low. And the next step is I visualized the data using Seaborn Python Seaborn library. I provided great visualizations. This is one of those where it compares the number of positive cases to negative cases, and from this visualization, it is evident that there is no class imbalance in this data sets, and so we need not do anything regarding that, and it is already optim. The data set is already ready to use. Related works. I had to do a lot of research before I could start doing my project. These are the five papers that I went through. The first one entirely talks about the different types of decision trees. The author herself has done a research of previous works using decision trees, and it is a complete report of the methods using decision trees. And in that, she has referenced another paper, which is the second paper, a novel frequent feature prediction model for disease diagnosis. In this, the author has proved that the prune decision J48 decision trees perform better for this task. compared to unpruned or simple pruned decision trees. So that is one of the findings from the second paper. The third paper is that the third paper suggests the use of C4.5 decision tree, and they have created a system called Mafia, which is good for predicting heart diseases. And the fourth paper is entirely based on feature extraction. They start with they create different combination of features, starting with three features, and then constantly increasing the number of features. And they also train different models on these combination of features, so that we get a different combination of models as well. Finally, they conclude that a set of 9 features are optimal for doing our heart disease prediction, and they have listed the top 3 models that performed well for this task. And the fifth paper the fifth paper talks about ensemble optimization. In this, they have they have used three three different three SVMs of different kernels. One is of linear kernel, one is of polykernel, another one is of radial basis function kernel. So they have stacked all these three SVMs, and that they have used bagging, in which the results are aggregated using voting, and then finally they are also optimizing it using genetic algorithm. They show very good accuracy in this method. So the method that I'm going to propose is almost similar to the fifth one, but the difference is they have used different kernels. There were only 3 SVMs of different kernels. What I'm going to propose is to use um, SVM of same kernel, but like 100 instances of it, and there's no need of using genetic algorithm also to improve the accuracy. So we'll see that in the coming slides. So methods. So I experimented with almost all machine learning, popular learning models. So starting with non deep learning models. So the non deep learning models that I trained and evaluated were random forest, logistic regression, support vector machine, naive Bayes, and decision tree. In that, decision tree performed the least. The accuracy was like 76.66, and the support vector machines and logistic regression performed the best. In that, the logistic regression gave an accuracy of 86.66 percentage. Then I went on to create my neural network, and initially it also gave accuracy of 78.33, and then I have to do a lot of fine tuning of model parameters to finally get good accuracy of 88.33. And then finally, after training these non-deep learning and deep learning models, I went to ensemble learning, where I combine multiple instances of the same model, and then the results of the predictions of all the models are aggregated using voting method, and the final prediction is given. So the model I used a SVM. So bagging, I initially tried using random forest, but random forest gave a maximum accuracy of 85%, and then I chose support vector machine. So I initially started with 50 estimators, and I kept increasing. In that, 100 uh, uh, a combination of 100 estimators proved to be a very efficient setup. So I'll be talking about it in the coming slides. And the results. So these are the top 3 models the top 3 models for this task. Logistic regression gave an accuracy of 86.66. Neural network gave an accuracy of 88.33, and bagging SVM method gave an accuracy of 90%, which is the highest. So this table shows the list of classifiers that I trained and evaluated, and the corresponding accuracies. Moving on to discussion. So In discussion, I like to walk through the entire process that I went through to do this project. So initially, after loading the data set, I had to do the pre-processing, which I already discussed, where I have to convert the labels to labels that suit the binary classification problem. Convert the labels from 0 to 4 to just 0 and 1. Either heart disease is present or heart disease is not present. And then I had to deal with the null values where so already I discussed there are two methods, either substituting the mean values or either removing this records altogether are the approaches. And since there are only six records in uh, our data set which has null values, I just removed it because that is the optimal step in this. And then once we have done with the pre-processing, I visualize them so that we'll get a good understanding of the data, and if there is any class imbalance, we have to handle that. So using data visualization, we can figure that out early on. And fortunately, we didn't have any class imbalance. So I had to, after doing data visualization, I went on to split the data in 80-20 ratio, where 80 is used for training and 20 is used for testing. And so after doing all this, after we have the data split, we are we are ready to train our non-deep learning models. I also defined so let me show the segment of the parts. So I also define evaluation tools like plotting confusion matrix. The confusion matrix that is provided inbuilt by scikit-learn is not very visually appealing, and it is very difficult to follow. So I wrote this method to plot the confusion matrix in a visually appealing way. And then I defined a common function to evaluate models so that I can reuse this thing. So where we are printing the classification report, and then I'm plotting the confusion matrix as well as giving an accuracy score for all the modules. So so let us go to non-deep learning models. So I started with random forest, and I ended up with an accuracy of 81.66, and this is the resulting confusion matrix. And then I went to support vector machine, and I got an accuracy of 83.33. This is the resulting confusion matrix. And then the third one is the decision tree. In decision tree, performed the least or the worst actually. So it gave an accuracy of 76.66, and this is the resulting confusion matrix. And then I moved on to naive Bayes, and it gave an accuracy of 80%, and this is the confusion matrix. And then came the surprise package, the logistic regression. So I trained it and I predicted and I evaluated it, and the resulting accuracy was 86.66 percentage, and this is the confirmation matrix. So training these non-deep learning models was a breeze since scikit-learn handled most of the parts. All I have to do is just use them and train, and then have the data available to train it and evaluate it. So it was really easy. The only thing I have to do is mostly like getting the data ready, and then having this method to generate this evaluation metrics. And then next step is tuning neural networks. So once I've completed and I evaluating all the non-deep learning methods, and we concluded with an accuracy of 86.66. So I wanted to increase the accuracy. So I went on to build my neural network. So I thankfully we have Keras, which allows us to create a neural network faster. So I wrote these functions to create the neural networks. One is create model, where we can define where we will create the layers. We'll add layers and we'll add the optimizer and then compile the model. And then I also have in this along with that classification report, I also added plotting accuracy loss curve and accuracy curve for neural networks. And this model, this function will do everything. It's just starting from building to training to evaluating and plotting. So there's one method that takes care of everything. So so I started with a single hidden layer of 26 neurons and activation function ReLU, and with optimizer Adam, I just got an accuracy of 78.33. Since we know that neural networks give optimal accuracy only if we fine tune it. So we cannot say which is the correct config or which is the optimal configuration right on. We had to do some alterations to find out the best configuration for us. And then the next step, I doubled the number of neurons to 52. The result was accuracy reduced. It went down to from 78.33 to 75. So that is not a good approach. So in the next step, I resetted it to 26 neurons, and what I did is added another layer of 26 neurons, and the accuracy again reduced. So this wasn't a good approach. And then the next step, I increased the number of epochs from 200 to 200 from the default 100, and there was no improvement as well. So after doing 4 steps, and I was like, uh, I understood that these are not the direction that we have to go. And then came the concept called dropout layers. Dropout layers is a great concept where we can create a layer of drop in which we can specify how much of the neurons can be dropped out, which means uh, uh, dropout means like the person that we mentioned, those neurons will not participate in the back propagation or forward passing of gradients, forward passing of the weights. So if we drop out 0.3%, then 30% of the neurons will be dropped out and they won't be participating, and they are selected by random. The other neurons will be participating it. So after adding a dropout layer of zero point 0.3, there was a drastic improvement of 6.67%, and the accuracy went on to be 80%. So I thought this was a good step. And then I increased the dropout to 50%, and the improvement was 3.33. It went on to 83.33. So just from zero point 0.3, I changed it to 0.5. And again, I tried to increase the number of neurons to 52. Again to regret it, because again, uh, it started to overfit and the accuracy reduced to 78.33. So till now, increasing the number of layers have never benefited us. And then the next step I tried is like the change has been very flat. There is no much improvement in the accuracy. So I changed the direction by changing the optimizer to stochastic gradient descent. Initially we had Adam, so I had to change it to stochastic gradient descent. And to my surprise, there was an improvement of 5%, and from 80 to 85 percentage. That was a great sign that the stochastic gradient descent is a great optimizer for this problem. And then since there is another option of RMS prop, I tried that as well, but it didn't. It wasn't suitable for our application, for our task. And so I fixed my mind that STG is the best optimizer for this problem. And in the next step, I added another dropout layer of 0.5, and I got an improvement of 3.33 over step 8. And that is from 80% to 83.33. The step 11 gave us the best result with three hidden layers, and two dropout layers of 2.5 each. That is 50% of their neurons are dropped out. And then optimizer was stochastic gradient descent, and epoch was 200. The accuracy was 88.33, the best ever. Even the logistic regression gave us 86.66, but this surpassed logistic regression by, I think, more than 2 percentage. And then I did further improvements, like increasing the number of layers and increasing the dropout layers. But and also I changed the activation function from ReLU to ELU. ELU is another activation function that is actually optimal. But the accuracy was constantly at 86.6 when I used ELU. So whatever I did, I couldn't increase the accuracy more than 88.33. So usually neural networks learn well when they are when they have large amount of data, and we have just 297 records of the patient, so that won't be a sufficient amount of data for neural networks. So we ended up with an accuracy of 88.33. The next one is next I went on to experiment with ensemble learning. So ensemble learning is the process of stacking multiple machine learning models together and giving them data of the same data set which are independent, and then getting the prediction out of it, and then aggregating the prediction to give the result. So there are two techniques in which stacking and bagging. So in stacking, we are using heterogeneous classifiers. That means we are using different classifiers. While bagging, we use the same classifiers but multiple instances of it. So first I used stacking, in which I stacked support vector machine, naive Bayes, random forest, logistic regression, and then I kept a voting hard. So voting is a process of aggregation. So if it's hard, then it means like you have to decide the prediction based on the number of votes, majority of votes. So the result given by each model is seen as a vote, and the class which gets the highest number of votes is selected as the prediction, final prediction. So I chose hard, and I got 86.66. I tried many instances, but I don't have that output here because I've deleted it. I'm sure only this, because this is the highest that I could get from stacking method. And then the next method, I went on to bagging. So bagging gave the cut. So in bagging, I started with using random forest, since we are using homogeneous or same multiple instances of the same classifier. I started with random forest, and then I gave the number of estimators as 50. I got I got an accuracy of some 83%, and then I changed it to 100. I got 85%, and if I increase further, the model started to overfit, and the test accuracy started to decrease. I started to go less than 85%, so I stopped it. And whatever I did, I couldn't get go past 85% for random forest. So I thought I could use SVM, because it performed well when I trained the non-deep learning models. SVM performed well, so I started with a support vector machine, and even I tried the same thing with 50, 100, 150, and 200. As I increased more than 100, it started overfitting even support vector machines. And but if I keep it 100, I get an accuracy of 90%, which is the highest in this experiment. So the other parameters that we use is max samples, which means you use 60% of the data as booster samples. So in bagging, how data is fed to each model is like you take a chunk of training data, 60%, and for each of these models, there will be the combination, or the order will be different, and different order and different combination of records will be fed. And max feature is like uh, how many feature you want to take at once. So that is one feature. So bootstrapping. So after bootstrapping, each model is trained, and then the prediction is given, which is aggregated later. So using bagging, we got an accuracy of all-time best of 90%. Also, I did feature extraction. Feature extraction. I wanted to do backward feature elimination, that is starting with all 14 features, and then iteratively delete features if they had less importance, or they didn't cause any change in the they didn't have a significant impact on the prediction. So I started doing that, and but due to this time frame, I couldn't complete it. Actually, I couldn't show my results over here. So it is definitely a work that can be done in the future. So this is this sums up my experiments that I went through in this project. Future work, and definitely feature extraction is one thing that interested me very well. But I need to create a lot of I need to create I need to keep testing and experimenting it with by deleting. Um, deleting deleting the features progressively, but and it will take a lot of combinations before we could try on different models. So it needs some time. So it is definitely a thing that we can see in future. So in future work, we have to start with feature engineering because having these 14 features together is not working out well. So if we start with feature engineering and if we delete some unwanted features and add some useful features as well, and then if we apply ensemble learning over it, the accuracy will definitely improve. The accuracy will definitely go above 95%, which is a very good accuracy for a predictive system. And then data set, definitely the data set of 297 records is not enough for any model to learn much. So since there are like four data sets inside a start data set in UCI itself, we can try to augment all the data sets together to form a single data set. So once we augment all the data sets, then our model will be able to learn from a large number of records, maybe more than 1,000 records. So that will be a huge that will be a good amount of data to learn from. So that is one of the future work that we can do in this in for this task. Conclusion: yes, I was successful in improving the accuracy from getting the lowest accuracy from decision tree to getting of 76.66% to getting the highest accuracy of 90% by bagging SVM. The improvement has been great. And then, but this is not the best. There is still a lot of scope for improvement. I'm sure that a lot of researchers are working on to get great accuracy, and there are greater accuracy too. So there is a lot of improvement in this task, and we can get nearer to 99 or 95, 99.5% if we try to we combine four techniques together. And message to I like to give some realizations that I um, that I got from this project. The first thing is definitely the feature extraction. So whoever is going to work on this task in future, always start with doing the feature extraction, and then proceed further. Also, try to augment all the data sets that are available in UCI, the four data sets, and then start working on the problem so that you can converge to a good accuracy faster. Um, than what I could achieve here. So doing this project was a great experience. I came across many classification accuracy improving techniques and classification problems, and I also got a good sense of this problem domain of what was done earlier and what I have proposed wrong, and what could be done in the future. So it was a great experience, and more like a research project. And I wish luck for the future researchers who are going to work for this task. And I hope that one day we'll be able to achieve 100% accuracy. Thank you so much for listening to this video presentation.